Hello everyone. Today we're going to start section 15.5. Talk about the surface area. Okay, we talked about the surface area before. I think we talked about a special case, surface of a revolution. We use integration function one variable. Okay, now this is different. We have a surface in the space. And later on, we're going to talk about the surface area again in the more general case. Okay, so now let's talk about this short section. Okay. Okay. Math 1D. This is a lecture 19. Okay, so this is a section 15.5. We talk about a surface area. Okay. Now let's look at a case. So here we say, suppose we have a surface in the space. Okay. Suppose this is surface in the space. And then we say, well, this is the coordinate system. Okay. Let's see. Well, how about if we put it coordinated this way? Suppose we're going to say suppose. Okay, how about this? I'm going to put everything in the first octant. And here, suppose this is the x-axis. And then this is the y-axis. Okay, how about that? This is the x, y, z. Okay, we say at a point. Okay, well, if we do partition, okay, suppose this is this surface is over a rectangular region, okay, rectangular region, and at a particular point, okay, so if we do partition, and then we're going to have something like this, so we're going to have a small patch. Okay, so here we have this small piece. Okay. Okay, let's draw a small rectangle. Okay, like that. And then if we said this is this point is x, I, y, j. Okay, so you see here. Suppose this is the xi, okay, of course this is the xi plus 1. And then we say, yeah, I think I'd say here is like this. Okay, so we said this is a delta x. And then, of course, here we say this is a yj. And yj plus 1, yj plus 1. Excuse me. And then, so this part is delta y. Okay, so at this point, this is suppose the xi, yj is a corner point of a small rectangle after we do partition. Okay, now, on the surface, suppose we say this is the tangent plane at this point. Suppose we have this tangent plane. Now the surface is like this. Suppose we say the surface is like this. Okay, that's a surface, and on the top is a tangent plane. Okay, so we call this a point Pij. Point Pij. Now, this part. So here we say this part. We call that delta S ij. Okay, suppose this surface is a S. And then we say this on the top of this horizontal tangent plane. How about we say delta T, capital Tij? Okay, so we have this. Now you see, if we say this is the equation z equal to f x y. It's like that. Okay. Okay. So here we say, well, this delta Tij, okay? So, well, this is the area of the tangent plane. Now, of course, this is approximately equal to this delta Sij. Okay? If the function is smooth, let's say you have a continuous partial derivative. Okay, so that's approximation. Of course, when delta x, delta y are small, it's a good approximation. Okay, so now we say, well, when we put this a area of S, the whole surface, so that's equal to the limit. So we say when n approach to infinity, so we have a summation I from 1 to m, j from 1 to n. This is delta Tij. Delta Tij. Okay, so we say that's the limit of summation of approximation. Okay, now let's see, how do we find a Tij? Okay, so if we separated this, we say Tij is like this. So here we say, well, suppose we have a Tij. Okay, so let me make it larger. Okay, extend a little bit. Okay, suppose this is a, and then we say, well, suppose this is a coordinate system. Okay, so here we have, this is a coordinate system. And then, how about we say, well, something like this. Okay, now when you think about this, then we say, suppose this vector, okay, suppose this vector is a, and this vector is b. This vector is b. Now let's see, how do we write the expression of a and a b? Okay, so if you see, I draw a right triangle, and then so this side is a delta x. Now this offset over delta x should equal to f prime. The partial derivative with respect to x at xij. So that means this part is equal to f sub x at xi yj times delta x, because this one over delta x is equal to the partial derivatives. And then, well, here is the same. Okay, we draw a line parallel to y-axis. Okay, so this is the right angle. Now we say, of course, this part is delta y. And then we say, well, this part is f sub y at xi yj delta y. Okay? Then we say, now we can write this, say here, we say A, this vector, is equal to delta x times I, that's in the I direction. And then in the k direction, well, because this is this is first triangle I draw here as a vertical plane perpendicular to xyz, perpendicular to xy plane. Okay, perpendicular xy plane. So that means it's a vertical plane. Well, perpendicular to y-axis actually. So perpendicular y-axis is a y coordinate is not changed. So that's the coefficient j is not there. If you want, it's to put it 0 times j, and then plus the vertical increase f sub x. So we say this is a f sub x xi yj and delta x k. And then part b, the vector b is equal to delta y j. Well, if you want, because this vector is perpendicular to the x-axis, so that means the coefficient I is 0, 0i plus delta y j and plus f sub y xi yj delta y k. So it's like that. Okay. Now we know the area is. Then we say this delta Tij. Okay, that's the area of parallelogram. So that's equal to what? We know is is equal to the magnitude of cross product, right? That's a geometric interpretation of magnitude of a cross product of two vectors. That's equal to area. Okay. Now, then first of all, we calculated this cross product A cross B. Okay, we use the formula. The formula say here is I J K, right? And then here, of course, delta x 0, f sub x at xi yj delta x, and then 0 delta y f sub y xi yj delta y. Okay, so we calculated this determinant. Okay, treat the I, J, K as numbers. Okay, so this is not this is not hard to verify. This is equal to. So, well, I'm not going to do the detail. You do the modification. Say you multiply out, and then you're going to have a negative f sub x xi yj times I, this vector, minus f sub y xi yj times j plus k, and then put a common factor delta x delta y. Okay, please verify this. Okay, now we say, well, the magnitude of this one, so here we say the magnitude of A cross B. Okay, so that's equal to square root, okay, coefficient I squared. So this is the fx xi yj bracket, or with the negative sign or without negative sign, doesn't matter, plus f sub y xi yj squared and coefficient k k is 1, 1 square is 1, taking square root. Now this part, delta x, delta y is outside, so the is positive, delta y, delta x multiplied together is positive, so you can just put outside. Okay, so that means we have what? This is the delta Tij. So if I substitute into the limit of summation, so we got this, we got the area of S is equal to limit m n approach to infinity, and then summation I from 1 to m, j from 1 to n, and then this is the square root of f sub x x I y j squared plus f sub y x I y j parenthesis bracket squared and a plus 1. And then, well, this we can just call it delta A. Okay, that's the area of the rectangle, length, delta y, width, delta x. Okay, now this limit we say may or may not exist. If it exists, okay, so you can see that's a limit of Riemann sum. It is a double integral. Okay, so that's a double integral. Okay, so we say D is a planar region. The surface is defined on. I didn't draw on the graph. Okay, so that's say directly under the surface on the xy plane. That's the planar region, and then the integrand, we just change this to f sub x of xy. Okay, squared plus f sub y xy squared plus 1. So that's taken square root. That's the integrand. And then here we say dA. Okay, dA. Now, a lot of times if if we say z equal to fx, so we have this A area of surface S is equal to the double integral over D, and then we have, well, we can put a 1 in front, and then partial z partial x parenthesis squared plus partial z partial y parenthesis squared, and then taking square root, and then we say this is a dA. So that's the formula for surface defined on D. Okay, we calculate surface area formula. Okay, so this is the formula. Yeah, I think that please make sure every step makes sense to you. Okay, the derivation. Well, I didn't do the every single step. Like I said, first of all, we do partition. We partition on the x-axis. Say for example, if x is between A and B, we do partition, and then let it I from 1 to m. We have x0 equal to A, x1, x2, all the way to xm equal to B. And then on the y-axis, y is between C and D, we do partition. So y0 equal to C, less than y1, less than y2, all the way less than y sub n is equal to D. Okay, and then we say on the small patch. Okay, so we say xi to xi plus 1 and yj to yj plus 1. So we do the approximation. We use the tangent plane, okay, at the corner point to approximate the delta S, the surface under the tangent plane. Well, when you look at it, the approximation, you can imagine when delta x, delta y are small, so the approximation is good. We assume the partial derivative exists continuous, so we say smooth, which means when we take a limit, and the approximation get better and better. Okay, Yeah, I think that the formula, once you understand the derivation, so it's not hard to memorize. Okay, now let's just look at one example. Okay, example, we say find the area of the surface the part of the sphere. Okay, the sphere is x squared plus y squared plus z squared equal to 4z. That lies inside the paraboloid z equal to x squared plus y squared. Okay, we have a sphere. Okay, we can write the sphere in the standard form. Okay, so we can do that right away. Okay. So if you look at it, this say x squared plus y squared plus z squared equal to 4z. How about I move this 4z to the left hand side and add 4 to both sides of the equation? Okay, so this becomes what? Becomes the x squared plus y squared plus parenthesis z minus 2 parenthesis square equal to 2 square. So this is sphere centered at 0, 0, 2, radius is 2. Okay, now the paraboloid z equal to x squared plus y squared. Okay, well, let's just draw the graph. We don't have to draw the completed part. We draw part of it. Okay, so here let's see. Okay, well, one thing is if you look at it if you look at the intersection of those two, where it's intersect. So if you substitute this z equal to x squared, okay, we say substitute z equal to x squared plus y squared into x squared plus y squared plus z squared equal to 4z, then you're going to have what? You're going to have z plus z squared equal to 4z. Now, this is, you cancel 1z, move 3z to this side, so z times z minus 3 equal to 0. Okay? Now, of course, this one, the intersection, so that means either z equal to 0. Well, you see both the surface pass through the origin, and then or z equal to 3. Okay, so that means the intersection should be at z equal to 3. Now you see the surface is z equal center at 0, 0, 2, radius is 2, so that means like this. And then here we say suppose this point is 0, 0, 4. So the surface should pass through this point. That's the center. So this is 0, 0, 2. Okay, and then now you see z equal to 3 should be here. So that means z equal to 3. Now, if you think about z equal to 3 on this paraboloid, so you have a x squared plus y squared equal to 3 squared or equal to root 3 squared. So that means here you have a Okay, so here we have this circle. Okay, how about we put it like this? We have this circle. Now this circle, of course, is x squared plus y squared equal to 3. Of course, z equal to 3. Okay, and then this is a part of the sphere. Okay, and then this is the y-axis, this is z x-axis. Now, if you want to draw the paraboloid is like this. Paraboloid, okay, like this. Now, so we said on the top, this is a part of x squared plus y squared plus z squared equal to 4z. And at the bottom, this is z equal to x squared plus y squared. Okay, so this is the x, this is the y, this is z. Okay, so the surface we're looking for is this. This is the S. That's the S. Okay, so it's let's say it's inside of the paraboloid. Okay, now if you want to find the area surface, you need to see where this surface is on, or we say if you projected this to the xy plane. If you project it to xy plane, you are gonna have this okay, circle. Yeah, I think okay. We say, well, this, how about we share this part? This is the D part. So that's the D. Okay. Okay, so now we say the surface, the area surface S is equal to, okay, so D, and then here we say we're going to have a 1 plus partial z partial x squared plus partial z partial y parenthesis squared, taking square root. And then here's a dA. Now what is a z? Okay, so here the surface, when we have this x squared plus y squared plus z squared equal to 4z. Well, remember this is equal to x squared plus y squared plus z minus 2 parenthesis square equal to 4, right? And then this means, say, z minus 2 is equal to, of course, here z minus 2 is a positive, the upper half of the sphere. So that's, we only take a positive sign. So that's equal to 4 minus x squared minus y squared. So like this. So that means we say, well, this surface, the equation is z equal to 2 plus root 4 minus x squared minus y squared. Okay, and then we say this partial z, partial x is equal to, well, constant derivative equal to 0, so that's equal to, okay, so here is, you calculate derivative, 4 minus x squared minus y squared. Okay, you have a 1/2 moving in front, but here you have a negative 2x, cancel the 2, you have that. And then partial z, partial y is equal to negative y root 4 minus x squared minus y squared equal to that. Okay, so now if you look at this, so here we say root 1 plus partial z partial x squared plus partial z partial y squared. Okay, so when you plug it in, you are going to have this is equal to what? Root 1 plus, here is x squared, 4 minus x squared minus y squared, plus y squared, 4 minus x squared minus y squared. Okay, of course, if you combine the three terms, so we're going to have this combine three terms, and then you're going to have a numerator just equal to root 4 is 2. Denominator is a root 4 minus x squared minus y squared. So we have this. Okay. Now, because we have already, if you put it this parenthesis and then plus, so you have x squared plus y squared. And then the d, if you look at this region D, maybe is best to write the integration in terms of polar coordinate. So this D, you see this D is r theta. And then theta is between 0 to 2 pi. And then r is between 0 and root 3. Root 3. Because this circle is x squared plus y squared equal to root 3 parenthesis squared, equal to that. So then we say this area of the surface is equal to 0 to 2 pi and 0 to root 3. Okay, and then this integrand, okay, that's equal to 2 over root 4 minus r squared. Well, dA is r dr d theta, right? So we have this. Okay, now this, you see the integrand is independent of theta. So this whole integration is independent of theta. So you can move out, and then from 0 to 2 pi d theta, that's just equal to 2 pi. Okay, and then 2r dr is equal to dr squared, right? Okay, so here we have a 3. And then we have, this is say 4 minus r squared to negative half. 2r dr is equal to dr squared, dr squared, dr squared. But I can put it, this is a 4 minus r squared, and then put a negative 1 in front, right? Okay, because d 4 minus r squared equal to negative 2r dr. Okay, we do have the 2r dr. This, let me write it this 2 better. So this is a 2. Okay, so the antiderivative, so here 2 pi. Okay, if we put it this negative sign out, now we know u to negative half du, the antiderivative is equal to 2u d u to half. So that's 2 4 minus r squared to positive half. So you think about calculate derivative, this half come down, cancel this one, and then d of 4 minus r squared. And then so here we say this is a root 3, and then 0. So that's like this. Okay, so here we're going to have what? You're going to have this is equal to negative 4 pi. Okay, and then when you plug in root 3 squared is a 3, 3 minus 4 minus 3 is a 1, 1 taken square root is a 1. When you put it 0 in as a 0, so 4 to minus 2. So that's equal to 4 pi. So if you use a polar coordinate, the integration is pretty simple. Okay, so this is this problem. Okay, where we say the area of the surface. Okay, if you want to give an answer and then say answer, the area of the surface. Well, when I say the surface, that's to say the part of a sphere inside the paraboloid is 4 pi. Okay, so yeah, I think I said here we just talk about one formula. You should understand the derivation of the formula. Yeah, I think most of the time I try to derive the formula. I really hope you follow step by step and then understand the derivation of the formula. Because if you just memorize the formula and then don't understand derivation, you use it, sometimes may not be very good. Because if you understand standard derivation, and then a lot of times in application you need to set up the integration by yourself, then you have a better understanding of the formula, so it's easier for you to set up. So please understand the derivation of a formula and then know how to use it. Okay, of course you see here we say the surface defined above xy plane. Sometimes you may think about it other way. So for example, the problem number 23, this section only has 24 problems, 23. Then you need to think about it, the surface is defined above xz plane, or you project the surface on the xz plane. That's your region of integration. Okay, so I think one example, if you really understand it, I think that's enough. So please read the section carefully and do the homework problem. Okay, so I'll talk to you tomorrow. Bye bye.